Hello, everybody. My name is Masood Olia, and I'm a professor here at Wentworth University in the School of Engineering and in the Mechanical Engineering program. And I'm back after a while with another problem. This one entirely related to the topic of statics. And here, as you can see, we have a beam which is 6 meters long, right? And it's under the action of a uniformly distributed load. 600 newtons per meter is the intensity of the load. And then it's supported by a pin at A. As you can see, I made it a different color to say these are pins. And then by this link, by this bar, BC. So B is a pin, C is a pin. And the objective here is to find the reactions that are developed at these pins, pin A, B, and C. So this is really a simple problem. You just have to be careful as you draw the free body diagram. As always, anytime you're trying to do, and this fits in the category of a two-dimensional rigid body equilibrium problem, you need to draw a free body diagram, obviously, and I'm going to do that now. So we know that we have a pin at A, so that gives us two components of reaction, AX, AY. As you know, we just assume they are in the positive directions. And after we solve the problem based on our equations, we can determine if these are the right directions or not. Basically, if you get positive answer, the directions are okay. If you get negative answer, you have to switch the directions. Okay. So now, let me go ahead and change this 600 newtons per meter to a concentrated load just for the sake of finding the external reactions. In other words, the reactions at A, B, and C. You guys know that that would be the area under the load, or area of this rectangle in a way. So that's just 600 newtons per meter. That's the intensity here times the length, which is 6 meters. So that's 3,600. And clearly, at 3,600 newtons, clearly you have to put that right through the centroid of your shape. So centroid of a rectangle is right in the middle. So that would be 3 meters from each end. So now the question is, what do we do with this guy, with B? So the first thing comes to your mind is that, yeah, B is a pin. So I'm going to have a BX and BY, right? I'm going to actually erase this, and because this is not correct. Well, it is correct in a way, but that's not the way we approach it. We're going to have a problem. So when you look at this situation, you say, oh, look, I have 4 unknowns. So there must be something wrong, because remember, we are limited only to 3 equations. Let me list them here for you. For a 2D problem, we can balance forces in X and Y. That would be 2 equations. And then you have a moment equation. You can take moment about any point you want. So you're limited to these 3 equations. So what's going on? Now, it turns out that BC actually is what we call a two-force member. So very important. BC is a two-force member, which means the force has to act along BC, right? Kind of like each member of a truss is a two-force member. So sorry for the mess here. I have to get a better eraser than my fingers. So what's happening then is the force will act along the bar. And look, we have the slope of this guy, which is 3 to 4. And that will help us to break it into components. I just want to clean that up a little bit for you guys. So just stay with me for a moment. So I have, as I said, I have to get a better eraser than just a piece of paper. But it turns out that actually the paper works better for this light board. Anyways, get rid of BX here too. So now we are okay, because we have, see, before we had 4 unknowns, we only had 3 equations. Now we have 3 unknowns, and we are all set. So typically what you would do is you would take moment about the pin, and that's what I'm going to do, and that way you can solve for FBC. So I'll take counterclockwise to be positive. So notice that if you break this guy FBC into two components, right, one like that and one like that, right, this would be the 3/5 of FBC, and this one would be 4/5 of FBC. And then you can get rid of the FBC. The 4/5 FBC, the x component passes through, it doesn't have any moment. So that leaves us with the moment of the 3/5 of FBC, right, times 4, right, where it's acting, 4, and that's going positive counterclockwise. Then 3600 tend to rotate about A at the clockwise direction, so that's negative. So actually, we don't have to use a calculator here. What I do usually, I say, oh, these guys cancel. 4 goes to 3600, 900, and then basically FBC becomes 5 times 900. So it's better to just not to use calculator till the last minute. Okay, we got the FBC. And then I'll show you how that FBC translates into the reaction BXBY. It would be really straightforward. Let's go ahead now and continue with this and apply our force equations now and find AX and AY. So we come over here and we say, okay, now let's balance forces in the X direction, right? And we always refer to your free body diagram, guys. So you have an AX. We assumed it's in that direction. We might be wrong, but it turns out that we are actually right, because that has to balance this 4/5 FBC. So minus 4/5 FBC equals 0. Therefore, AX becomes 4/5 of FBC. Now remember, FBC is 4,500, not 3,600. 4,500. And that becomes 3,600. Positive. Implies that, first of all, the unit is newtons and the direction is okay. So far, so good. In the y direction, similarly, we try to balance forces. We pick that to be positive. So look, we have AY. We have the 3/5 of FBC, right? And don't forget the 3,600 load. Again, if you put 4,500 here, 3/5 of 4,500 becomes, this is by the way positive, sorry, pointing up. So this becomes 2,700 minus 3,600 becomes minus 900. Eventually that becomes a positive 900, which implies that the direction of AY is also okay. Now, by the way, sometimes you're asked to find the resultant pin reaction at certain pins. So in this case, if I ask you what is the resultant pin reaction, basically you have two components, a 3,600 and a 900. And then this guy is the resultant, which I call it F sub A. This later on, when you take mechanics of material course or you're interested in the topic of stresses, shear stresses at the pin, becomes critical, because you need to use this F sub A or resultant pin reaction in general to be able to figure out what shear loads are acting at the pin. So F sub A in this case would be square root of 3,600 squared AX, right? And AY squared, which becomes, I believe, 3,710 and some change, 0.8. And that's newtons. Now, to wrap this problem up, guys, we were specifically asking what's going on at B and C. Well, basically, we figured that this rod BC is in tension and the load that is acting on it is the 4,500 that I calculated here. So let's take a look at this. So, see, this is basically what's happening. This is the 30, I keep saying 3,600. This is the 4,500, guys, right? In that bar. So, look, it's very easy for me. So this is B and this is C. So this is really BX and this is BY. And this is CX and CY. Obviously, CX and CY must be equal to BX and BY respectively. So BX equal CX equal what? Based on the slope, I didn't do a good job here with the slope. This doesn't look like a 3/4. But anyways, that would be the 4/5 of the 4,500, which is 3,600. And similarly, Cx must be equal to Cy. By must be equal to Cy. By must be equal to Cy, right? So this guy must be equal to this guy, and Cx must be equal to Bx. And that should be then 3/5, 3/5, right? Of 4,500, which actually becomes 2,700. All right. I hope you enjoyed this video. This was really a quick two-dimensional rigid body equilibrium example, but the key point here was the fact that BC is a two-force member, and if you start with showing a BX, BY here, you're going to have a problem because we are limited to only three equilibrium equations. So as always, if you like this video, I usually make a lot of videos on different topics, statics, dynamics, mechanics of material, vibration, system dynamics, anything that is in the solid area. So if you like this video, please subscribe and put any comment you have. Thank you for watching, and I'll be back soon.